We have 2 classes remaining, so please do your best for the remaining classes. So actually the final exam covered just after the coverage of the midterm exam, and then the final exam will cover the what we learned in the next class. Okay, so actually it's just very simple. The coverage of the final exam is just after the coverage of the midterm exam. Okay. So so in the previous class we learned about the performance of the applications, which can be influenced by the configurations of caches. So actually this example is a very good example. So that means, so actually the cache structure is not it's not revealed to the software engineer. So that means that the software engineers or software programmers usually does not know about the configuration of the cache memory. But cache is very critical for the performance of computer systems. So that means the cache is very critical for the performance of applications. So in the previous class, we learned about the matrix multiplication. So actually, if the size of a matrix grows, then the cache may not be used in efficiency. That means that cache can be used inefficiently. Okay, because the data requested by this matrix multiplication may not be found in the cache because the cache size is small. So then we can change the algorithm of the matrix multiplication. So we can split the very large matrices into the multiple sub matrices. Then we can apply some modified matrix multiplication algorithm for this case. So with this modified algorithm, then we can increase the performance of our matrix multiplication. Okay. Also, in the previous class, I explained the very basic of the virtual memory. So actually, in this class, I will also explain about this virtual memory. But before starting today's class, many students asked about some addressing in the cache memories. So in this course, I explained that most of computer system use byte address. So what is a byte address? Byte address. So that means the address 1 just covers the 1 byte of data. That is byte address. But in this chapter 5, we sometimes use some word address or block addresses, like or block address. So what is word address? So in the byte address, the address 1 just covers the 1 byte. So and simply with word address, just address 1 covers 1 word. So usually I just provide the size of 1 word in the problem. So that means usually the size of a word is 4 byte. So the word address 1 means is just equivalent to the 4 byte. Okay. So address 1 just covers the 1 word. Very simple. So we can just divide the byte address with 4, that is the size of the word, to compute the word address. Okay, it's very simple. So it's actually byte address divided by the word size, the word address. And how about the block address? With the same manner, we can compute the block address by dividing byte address with the size of a single block. Okay, it's very simple. So address is a byte address divided by size of a block. That is block address. Okay, so it's very simple actually. So okay, let's learn about the virtual memory. So in the previous class, I explained that virtual usually means not real. So I believe some students maybe struggle to understand the meaning of a virtual because it's not real. It's not physical. So usually the virtual, the opposite meaning of the virtual is physical. So that means it's real. So we are learning about the computer system, actually the computer hardware systems. So this hardware, so that means that we are learning about some physical systems. So it's a real systems. But what is virtual? Virtual means just, it's not real. It's not real. So then why do you use virtual memory? So I explained why we use virtual memory in our computer system. So actually the virtual memory first invented to use the large memory, but even though the size of physical memory is very small. Okay, so actually this why do you use cache? If the data is stored in the cache, then the cache memory is very fast. It's faster than the main memory. So if the data is found in the cache, then we can access this data very quickly. So we can improve the performance. That is the main concept of cache or caching. Okay, caching or the main concept of cache. Then, so I explained that the actual memory, in the old computer systems, the size of actual main memory, the physical memory, is very small. But we want very large memory. Then, we can use the large memory. Where is this large memory? The storage. Okay. The storage is very slow, but the size of storage device is much larger than the size of main memory. So if we can use this storage space like a real memory, so actually this is the size of the very small physical memory, but we want to use the very large memory. So it's a software application. So software applications want to use very large memory. So where is this large memory? In the storage. The storage. So if we include the part of storage space in this memory space, this is memory space, not Microsoft, it's a memory space. Then, we can enjoy this large memory. What's the problem? the data is in this storage space, then access latency is very high. That means it's very slow. So what is the important goal of this hardware architecture? Performance. The performance is very low, then it's bad computer system. So we can store the required data in the storage space, and then actually this virtual memory space is provided by operating system, but software think that, oh, our computer system has very large memory, including real physical memory and the additional storage space. However, if the data is found in the storage space, then performance of this computer system may be very low. So the main idea of the virtual memory system is that we can use this physical memory like cache. So that means it's very simple actually. So why do you use cache? I repeat the question. If frequently used data is stored in the cache, then we can access this data very quickly. Then we can improve the performance. And it's the same to the virtual memory. So this is the memory space seen by this software. But under this virtual memory space, some data exists in the physical memory, and then some data exists in the storage space. So if the frequently used data is located in physical memory, then this software can access this data very quickly. Then how can you manage this caching mechanism between physical memory and storage space? So you can think like this. Oh, this is memory. So how can you access memory? We can access memory with address. Okay. So software access this memory space with address. But this is physical memory and this storage space. Some data can be mapped to the space in physical memory, or some data can be mapped to the data on the storage. Then we want to manage this mapping. Okay, because if this data is very frequently used, or this data is frequently used, then we want store this data in the physical memory. And then, this data is not used frequently. So this data can be stored in the storage space. So what does that mean? The mapping information can change. Understand? So I explained that with the virtual memory, then the operating system provides the very large memory space, but it's fake. So some space is provided by physical memory, and then some remaining space is provided by storage system. And then we want change mapping information to physical memory or storage. So this mapping information, so from the virtual memory to this real mapping, that is the address of the real data, can change. Understand? So mapping information can change it. So what is required? We require mapping information data. And then this data should be changed. So it is, so actually changed, it can be changed by software because it can be changed, I said. So actually this virtual memory is provided by operating system. Operating system is a software, right? So that is the main concept of the virtual memory. So it looks like this. So people explain about the benefit of virtual memory. So I will explain how the virtual memory is translating the address space in physical memory. So this is the virtual address. So this virtual address is seen by software. What does that mean? Oh, we can, what is software? Instruction, like load x1, 0, x2. So if we see this instruction, then we can know that with this address, this instruction just access the data in this address, and then this data is transferred to the register file. And then, so I mentioned address here. What is this address? It is used by instruction. So actually instruction is software. Okay, because our high level code is translating the machine instructions, right? What is this address? I said, oh, this is the address seen by software. So actually this address is virtual address. That means, no, it's fake. It's not real. So, and then as I explained, this virtual address is mapped to some physical address. So this physical address is included in the physical memory, like DRAM, real DRAM, or some virtual address space is mapped to the disk addresses. So that is the additional space provided by disk, like storage devices. Okay, so I believe someone have heard about the page on Windows operating system or swap space on Linux operating systems. So these are some temporary space provided by storage devices. So if the memory space is not enough, then some data is stored in this space provided by storage system, like swap space or page spaces, and the data is temporarily stored in this disk space. And then if this data is used by software, then that means that, oh, I said, oh, we can use the physical memory like DRAM, like cache. And then how cache works? If the data is referenced, the data is requested, then data is allocated to the cache, and it's the same. If the data is found in the space on storage devices, and then if this data is requested by software, then this data is moved to the DRAM, it's a physical memory. So this DRAM space is called the physical address space. So that just points the location where the data really exists in the physical system, in the real system. But to the software just sees virtual address space. So software think, oh, this is the memory provided by our computer system. And then software freely access data pointed by these virtual addresses. But this virtual address can be mapped to the physical address space, or the virtual address space can be mapped to the swap space or page space in storage systems. Okay. Then this mapping can change. So this mapping information should be required. Understand? So in a real computer system, like load instruction is executed like x1, 0, x2, or this is the virtual address. And then actually, in order to access the data pointed by this virtual address, this virtual address should be translated into the physical address. Because the data exists in real physical memory. So they may be confused. So software works in the fantasy world, it's a virtual world, but the data should exist in real world, like the physical world. So in order to access the data in the real world, this virtual address should be translated into the physical address. So which means software try to access this data with the virtual address, this address. Then in order to access this data is in the physical memory or disk, on the disk or storage system. Then we need to know the real location, the physical address of this target data, requested data. So this virtual address is translated into the physical address. And then if the physical address is done, then with this physical address, the computer system accesses the physical memory. So, oh, data is here. Then this data is transferred to the register file like this, because this is load instruction. Okay. So, understand? So this is actually virtual address. So virtual address. So you need to remember that virtual address should be translated into the physical address. Then how can we translate? This information is provided by operating system. But if we just translate the every byte address to the every byte address of physical memory, then it will be very inefficient, right? So every byte, so let's imagine like this. Every byte is translating to every byte of physical address. It's inefficient. It's very inefficient. And then also the application exhibits the locality. So that means that if the application accesses the data, then this data is grouped in some small address range. That is locality. So when the this virtual address is translated into the physical address, we just translate some coarse block of the virtual address space into the same size of a block in the physical address. And then this coarse block is called the page. And then usually the size of a page is 4 kilobyte. It's 96 byte. So this is the virtual address. So, and then, but this lower part, so this page part is not translated. So actually this large chunk, the page is translating the page in physical memory. So this part is not translated, the lower 12 bits, because usually the size of a single page is 4 kilobyte. Okay, this part is not translated, but the upper part is translated into the physical page number. This is so this upper part is called the virtual page number, BPN, and then this BPN is translated into the physical page number like PPN. And then the lower part, it's called the page offset. The page offset is just provided to the page offset of the physical address. So just this part is translated, virtual page number part. And then, so why do you use virtual memory? So originally, we use the virtual memory because the size of actual physical memory is very small. So that means the range of a virtual address is larger than the range of a physical address. So usually the virtual address field size is larger than the physical address field size, the size of a physical address field. So in this example, the virtual address field size is the 48-bit. Then what is the size of this virtual memory seen by software? So the virtual address size is the 48 byte. What is the size of virtual memory? It's fake memory seen by software. Actually 10-bit is kilo, and then 20-bit is mega, 30-bit is giga, 40-bit is tera. It's 2 to 10, 2 to 20, so 2 to 30, 2 to 40. So it's 48-bit. So this virtual memory size is 256 terabyte. 2 to 8 multiplied 2 to 40. Right? So the software thinks that, oh, this computer has 256 terabyte of memory. It's not real because it's a fake, but the operating system just provides this virtual memory space to the software. Then what is the actual physical memory size of this computer system? So the size of physical address field is the 40 bits, right? So what is 40? It's very large actually. 1 terabyte of memory. Okay. So the virtual memory space size is the 256 terabyte for this system, but actual memory size is 1 terabyte. Okay. The software think that, oh, this computer has 256 terabytes of memory. But some data is stored in the storage system, where some data exists in the real physical memory, like real DRAM. Okay. And then, but so you may think that, oh, virtual memory is actually originally invented to use the very small physical memory, but recently we have a very large physical memory, like let's say usually larger than 4 GB of RAM. Then why do we need to use this virtual memory? Why do we need to learn virtual memory? Why is it still used in our computer system, even though our computer system has very large physical memory? It is because if we use the virtual memory, then we can easily write our program, our software. So let's think about this case. So this is application, like for example, it's a Microsoft Word. But in the same computer system, we can load the same application at the same time, concurrently. That may be possible that we can launch Word and then we can launch another Word on our computer system. Okay, so binary is the same for this application. The binary is the same. So that means that the instructions are the same. Instructions in this binary file are the same, but we can launch multiple processes from this same binary file. Understand? Do you understand this case? So binary is a binary file. It's the compiled instructions. Actually, the compiled instructions are the same. So what does that mean? This is an example. So if the binary is the same, then load x1, 0, x2. This instruction is the same. So this is Word application. Word 1, this Word 2 launched on the same computer system. Binary is the same. Then how can you manage this case? This Word want to access some data in this memory. Also, does this Word try to access the data with the same instruction? What's the problem? Because these two processes are different. So, but the binary is the same, but processes are different. What does that mean? On the computer systems, application for this word, so it's process, I call process. If the processes are different, that means these different processes just like different applications. Okay, so different processes, it's just like a different software or applications. Even though the binaries is the same, the instructions are the same. So this is the same binary, but this word tried to access the different data, but address can be the same. How can you handle this case? So because the instructions are the same, address may be the same, it's the same, but we want access the different data. That can be possible because with the same word, applications are launched on the computer system, but these two different processes may access different data, but address is the same. So how can you solve this case? Different data. The address is the same, like load x1, 0, x2. Oh, this address is the same, but we want to access the different data because these are the different processes. We need virtual memory, a virtual memory space. So what does that mean? This is the word 1. This is word 2. And then actually the operating system provides the virtual memory space for this word 1 process, and then also provide the virtual memory space to this word 2 process. It's a process, and the virtual memory space of this word 1 process is mapped to the different physical location. Also, this virtual memory space of this word 2 is mapped to the different physical location for this virtual memory space. How? Oh, I said, in order to translate the virtual page number to the physical page number, the operating system needs to provide this translation information. And simply, if operating system provides the different address translation information for the different virtual memory space, then, even though this virtual address is the same, this virtual address of this word 1 is mapped to the physical address 1, but it's the same one. Virtual address 1, virtual address 1, same virtual address, but the virtual address 1 of this word 2 process is mapped to the physical address 2. It's different data. What does that mean? Software does not consider about the real physical location of data. If we just use the virtual address in our software, the operating system automatically map this virtual address to the separated physical address spaces. That is actually the real benefit of virtual memory. So I said the virtual memory was originally invented for handling the very small size of physical memory, but recently we already know that the size of the physical memory is very large. So why do we use virtual memory? If the virtual memory is used, then operating system just map this different virtual memory space into the different physical memory spaces automatically. Okay. So that means if the programmers for this real application do not need to consider how to manage real physical memory. So the management of this physical memory space is handled by operating systems, but the user application, the programmers for user applications do not need to consider about this physical memory management. Okay, so the programmings are not very easy, but it's relatively easy if we use the virtual memory space. Do you understand? So if this virtual memory is not provided, then the software engineers need to access the real physical memory space directly. And then it's actually ridiculous because the different computer systems may have different size of physical memory. How can you handle these different configurations with the one application? So it's not easy. Okay, so the user applications just access the virtual memory space, and then this mapping is managed by operating system because the operating system knows the status of current computer system. Okay, so actually this is the main benefit of virtual memory actually. So any questions? So it's not an easy concept because so actually the virtual memory is a fake, but it is a convenient concept. So it's if this virtual memory concept is used, then we can make our software very conveniently. Okay, so the caching is the main purpose of the virtual memory, the original purpose of the virtual memory, but recently the main benefit of by virtual memory is the just memory space management by operating system. Actually not. So, it's a very good question actually. So instruction is also the data. So it's case by case actually. So it's not easy concept. So sometimes some data can be shared by different applications like shared library, such as shared libraries. So in this case, the physical memory space can be shared by different virtual address space, but usually the instructions. So if we just handle the instruction, so actually the instructions are also stored in the virtual memory space. So just if you just find some slides in the chapter 2, then you can find that, oh, this is some memory space of the application, this binary file. You can find, oh, this is the text space, so text area, like instructions. And then these instructions are also stored in the virtual memory space. Okay, so instructions, actually we can say that, oh, instructions are also the same binary, but when the instructions are transferred to the main memory, then these instructions can be shared by different processes, or these different instructions are separately managed by different physical memory space. Okay. So if you just the chapter 2, I don't know some page number, but you can find that, oh, this is the virtual memory space, and then some instructions or some text data is stored in the some address range of the virtual memory, and then this is the dynamically allocated space, and then this is stack, and then so this is kernel space like this. So instructions are also stored in the virtual memory space. Okay, not so the instructions are also managed in the same virtual memory space for a process. Now, okay. Okay, so if you have additional questions, so I'll explain after the class. Okay, so I explain how the virtual memory is translated into the physical memory address. Like the page offset is the page offset is determined by the size of the single page, And then actually the upper part, like virtual page number part, is translated into physical page number. So then with this ppn plus page offset is the real physical address. So then I said this translation information is managed by operating system, because this is the actually software structure, not hardware structure. Of operating system managed this translation information in a real time. So this is actually software structure. Then how can we manage this mapping information? Like, oh, this is the virtual page number, and then based on this mapping information, this virtual page number is translated into physical page number. Simply we can use the, oh, it's the virtual page number 0, then this virtual page number is translated to physical page number 10, 100, like 100. Virtual page number 1 is translated to physical page number 1000, 2, 4, 300, 1001. This. We can manage this translation information with table. So this table is called the page table. So page table. Then how can you translate the virtual page number to the physical page number? So this is the entry number of the page table. And then if the virtual page number is given to this page table, then this page table has the physical page number information. So for example, if the virtual page number is 3, then you can just access the entry number 3 of the page table, and then this page table entry has the translated physical page number, like so 1001. Oh, then we can get the physical page number from this page table, and then page offset is just it's copied to the physical address. So virtual page number 3 is translating the physical page number. So this is the software structure, and then this page table information is stored in the DRAM, because it's software structure. And then the location of this page table is managed by page table register. Okay, so if the page table is located in the DRAM address 0x0010, then this page table register has the 0x0010, and then when this virtual page number 3 is given to the page table, then we access the address 0x0010 with this page table register, and then we can find the entry number 3 from this page table, then we can get the translated physical page number, like 1001. Okay. Also, this page table entry has the valid bit. So that means, so in this figure, you can find that some page is mapped to the physical memory, but some pages are mapped to the space in the disk. So what's the problem? If the data exists in this disk or storage device, the storage device is very, very slow. So first, the data in this storage device is transferred to the DRAM, like physical memory. So if this data is transferred to the DRAM, then it's newly allocated to the DRAM. So we need to also update this mapping information. So actually, in the page table, if the valid flag becomes the 1, so that means that this page exists in the physical memory, like DRAM. And if this valid bit is 0, that means this requested page exists in storage devices. So in this case, so if the valid bit is 0, then this case is called page fault. Page fault means that, we need to access this page with the virtual address. But when you access the virtual page table, the corresponding entry is invalid. So that means the requested page exists on the disk or storage devices. So in the page fault, we first transfer this page data to the physical memory. Okay, then we can access this data. So if the page table is in memory, then we can access this page table entry has the physical page number, and then it's valid, then we can access this physical memory. If the page is not present, then we need to access the disk, and then this event is called the page fault. So page fault is the kind of exception. What is the definition of exception? It's an exceptional event. So if the page fault happens, then the operating system just provide this page fault handler. It's also software, and then the exception happens in the processor. Then the page fault handler is called by operating system. Okay. So then if the page fault happens, the data in the disk is transferred to the main memory, and then the page table is updated because the data now exists in the physical memory, and then the request operation is re-executed. So if you remember how the exceptions are handled in the pipeline processor, it's very similar actually, because the page fault is a kind of exception. Okay. Also, another issue is how to manage frequently accessed pages. So in this figure, I explained that some the request page may exist in the physical memory, or the request page exists in the disk, but disk is very slow. So the physical memory is used like cache. That means the frequently used data should be located in physical memory. Then how can you manage this case? We can manage this physical memory like cache. So how can you manage cache? We frequently use least recently cache replacement policy. So that means if a certain data is least recently accessed, then the new cache block should be allocated. Then this block is evicted from the cache. And then actually the same policy can be applied to the virtual memory. So with the virtual memory, the frequently accessed pages exist in the physical memory, and then the infrequently accessed pages exist in disk or storage devices. So, but if some pages in this physical memory is not frequently accessed, and then new pages are need to be allocated, then this page should be evicted from the physical memory. Okay, but no, actually the physical memory size is very large compared to the cache. It's not practical to apply the real LRU policy, so least recently used replacement. Okay, so instead we just use the very simple policy, like the policy written like this. So there is a reference bit in the page table entry, and then these reference bits are periodically cleared by operating system. So if this page is accessed, then reference bit becomes the 1. But periodically this page, this reference bit is cleared. So if operating system just check that this reference bit, the operating system can detect the infrequently accessed page. Okay, so this is not exactly working, but we can apply the very simple mechanism like this. Okay. And then then what's the problem of the virtual memory? Another issue. So why do you use virtual memory? Because it's easy. If we use the virtual memory, then we can easily write a program. You don't need to consider about the physical memory space. You don't need to manage it. The programmers do not need to manage it, physical memory directly. What's the problem? What is the problem of the virtual memory? So where is the data? So data is in real physical memory. The problem is that in order to access data, we need to know real address, physical address. But software just use the virtual address. The problem is that whenever the software uses virtual addresses, these virtual addresses should be translated into physical addresses. And in order to get physical address, we need to access page table. And where is this page table? Page table is in RAM. Okay. So what's the problem? Let's think like this. It's a load x1, 0, x2. Oh, we know, oh, this is the virtual address. Oh, let's get data from the memory. But in order to access this data, we need to get physical address of this virtual address. How can we get physical address? Oh, we need to access the page table. And where is the page table? RAM. So in order to access data in DRAM, we first access DRAM for getting mapping information from the page table, and then we can get the physical address, and then with this physical address, we need to access the physical memory again. So what's the problem? Not access the real data, we need to access DRAM twice. So software think that, oh, I can just access DRAM one time, but in reality, in order to get physical address, we need to access DRAM, and then with this physical address, also we need to access DRAM again. The problem is that, oh, not get real data from the physical memory, then we need to access DRAM twice. You know, oh, DRAM is very slow. So for the performance, virtual memory is not good. Okay. How can you solve this issue? Oh, the data is in the DRAM. And then in order to access the DRAM, it will take a very long time. How can you solve this issue? Cache. So if the frequently accessed data is temporarily stored in the cache, then we can access this data very quickly. The same idea can be applied to the virtual memory translation. What does that mean? So so think like this. Oh. In order to get the physical page number, then we need to access the page table with the virtual page number. So this is the mapping information. And this mapping information can be cached. So this mapping information is cached in the processor, like L1 cache or L2 cache. Then, oh, and then if this information is found in this cache, then we can access this translation information quickly. So this caching mechanism or caching component is called the TLB. So TLB is the abbreviation of translation side look side buffer. So this page mapping information can be cached in TLB, translation look side buffer. So what is the benefit? So if this mapping information is found in the TLB, then we don't need to access DRAM for the page table, for accessing page table. So we can access this page mapping information very quickly. So it's good for the performance. Okay. So also the TLB has the TLB may have the hierarchical architecture like L1 TLB or L2 TLB. Okay. Also, this L1 TLB can be split into the L1 instruction TLB, L1 ITLB, or L1 data TLB. Okay. So the TLB is the cache of page table. Okay. And so this is the original mechanism of page translation. So we need to access the page table in the DRAM, but as the TLB is used, then we can first access the TLB. So it's the same to the cache. We don't, if if there is a cache memory, then instead of we access DRAM directly, then we can first check the cache, right? So the TLB has also the translation information, and then also TLB has the cache-like structure, okay? And then TLB is accessed by virtual memory, like not so virtual page number, okay? So accessed by this virtual page number. So like the cache, some part of the virtual page number used as the tag, okay? And then if the tag is matched, and then this TLB has the valid translation information, and then this is TLB hit. So if the TLB is hit, then the requested page translation information is found in TLB. So TLB can provide the translation information, and that's it. But TLB is cache, so the requested page translation information may not be found in the TLB. So in this event is called the TLB miss. So in this case, we need to access the page table in the DRAM. Okay. So with the TLB, we can first access the TLB with the virtual page number first. Okay. Then we can get the translation information directly. But if not, then we can access the page table in DRAM. This is the TLB miss. Okay. So if the TLB miss happens, then we need to access the page table. And this is miss. So what is the required operation for cache miss? Cache miss happens, then the new data is allocated to the cache, and the one of occupied cache block is evicted from the cache. And it's the same to the TLB. The TLB miss happens, we need to access the page table, and then the translation information is provided to the processor. And then this information is allocated to the one of TLB entries. And then the old data, old information is evicted from the TLB. It's the same, actually. But TLB is the specialized cache for the page translation information. You can just remember this. Okay. Okay. I also explain about the so like this TLB misses or page fault here. Then let's see how the TLB and cache interact with each other. So let's start from the load instruction. So if this instruction is executed, actually this is the virtual address. So in order to access the real data, then we need to translate this virtual address to the physical address. Okay. So when we learn about the cache, then we think that, oh, this cache is accessed by this address, but it's not true actually. The cache should be accessed by physical address because this is the real address of the real data. So what does that mean? So in order to access the cache, then we need to get physical address. So how can we get these physical addresses? We can get physical address from TLB or page table in the RAM. So TLB is the cache of the translation information, and fortunately, TLB has very high hit rate because of locality. Okay, so think like this. Oh, this is the data accessed by some applications, but one page size is the 4 kilobyte. And then usually if this page is accessed, then the following instruction will access the same page because of locality, right? So actually the TLB has very high hit rate, and it's very good thing actually. So in order to access the cache, you need to get physical address from TLB. Okay, so this is the virtual address, like load x1, 0, x2. Oh, this is the virtual address. And then this virtual, with this virtual address, we need to first access the TLB. So when the TLB is accessed, then we can get physical page number. So this lower 12 bits is the page offset. So with this page offset is, we can use the page offset directly, but in the upper part, we need the physical page number. So this is the physical address. Okay, and then with this physical address, we need to access the cache. So we can split this physical address field as the tag, cache index, and the block offset. Okay, so we can access the cache like this. This is the tag memory and then data memory of the cache. And with the cache index, we access the tag memory and data memory of the cache. Then we can get the data if the cache is hit. So this is the required operation, the real required operation for accessing cache. So what's the problem? There are many problems in the computer system. What's the issue? So you see is that, so we learned that the previous class, I don't know. So what is the purpose of Aaron cache? So actually, the Aaron cache size is small. Why? We want very fast memory. And then actually, for the Aaron cache, hit time is very critical because we want very fast memory for the Aaron cache. What's the problem? In order to access the cache with the physical address, we first need to access the TLB. The problem is that, so we just to see the AMAT, the average memory access time, then hit time is also very critical. But we first need to access TLB, the hit time may be increased. Then it's not good for it's not good for the performance. Okay, because we want very fast memory for the Aaron cache. So in order to avoid this case, we can access Aaron cache with the virtual address instead of physical address. Okay, but the L2 cache is usually accessed by physical address. Okay, so alternatively, we can use the virtual address tag for the Aaron cache. So this is the actually the true data access path with the TLB and cache memories, but because of performance issues, we can use the virtual address tag for the Aaron cache. Okay. Okay, so I will stop here. So in this class we learned about the also the virtual memory and TLB, that is the translation look-aside buffer. Okay. Also, I covered this cache summaries in the previous class. Actually, this is very important. So try to understand about these cache summaries. Okay. Okay. So do you have any questions about the virtual memory? Okay. So try to solve the homework for problems by yourself, because it's also very important for preparing the final exam. Okay, so then we have only one class. So next class will be the last class of this course. Okay, I'll stop here and then thank you for your attention. See you in the last class. Bye, guys.